Hi, I'm Ron Olch. I'm the systems engineer for the UFO camera project. I have a long history in electronics and computer development, design, and software. I actually have a master's in computer science and engineering from UCLA. I work for such diverse firms as Walt Disney Imagineering, Teledyne Controls, and AeroVironment, doing all kinds of electronics, software, systems engineering, and so on. I actually started a UFO research group back at UCLA in the mid-70s, which continued to meet all the way up until a couple years ago continuously. We had a small group of highly skilled engineers and scientists, and each of us had sort of a specialty. And mine had to do with instrumentation for ufology. I was particularly interested in the concept of collecting data in a verifiable way. As most of us know, the problem with UFO data, and particularly videos and photographs, is their history. You can see one, you don't know where it came from, you don't know when it was taken, you don't know where it was taken, you don't know what it's taken with. Furthermore, there's no ancillary data, metadata if you will, that what happened in the environment at the same time the photo or video was taken. For example, was there an electromagnetic signature that occurred simultaneously with the event that we might expect? We don't really know in the field exactly what that is, but we're pretty sure from other information that there are things like that that need to be collected. So there's all kinds of data like that that one needs to collect, and along with that, there have been in the past a number of attempts to build systems that can collect video and photo information. I don't know of a lot of this ancillary data that was collected with it, but there has been some really good attempts. However, it seemed to me when I started this a couple years ago that the results of those attempts were very expensive one-off collections of hardware and software that no one could reproduce, certainly no one could afford. They're really good for what they did. I don't know of a lot of data they collected. One of the problems with that, of course, is that the events we're talking about are sparse. We don't know exactly when they're going to occur, and if you dedicate your equipment to one site, because it's all you've got is one set of equipment, you may never collect anything. So the idea was to come up with a system design that was at once very flexible in its combination of equipment, and also could be therefore very inexpensive, and because of that we could deploy a lot of them in various ways. So what resulted from that is the system we're going to describe today, which is an overall, I call UFODAS, UFO Data Acquisition System, which consists of several different pieces of software, some custom hardware, but the minimum is nothing but some software that runs on a PC, and the minimal camera could be just a webcam. That's all it has to really be. Stick a webcam in your window, good to go. Or in a maximalist view, there could be multiple PCs in multiple locations communicating over the internet with some fairly sophisticated cameras, and another piece of equipment I developed, which is a box that has a computer and some data acquisition hardware in that to collect all kinds of these so-called ancillary parameters: temperature, pressure, accelerometer, magnetometer, and so on, as well as GPS. So now we can know what are these changes to these parameters when we simultaneously see something in the sky. Furthermore, one unique feature of this system that I don't think was done before was if we deploy at least two of these camera systems, then they can transmit their data, either the camera or this ancillary data collection system, that may be co-located with the cameras or not, and all that data goes through the internet to one place we call mission control, and at that place the data from the cameras can be triangulated to point to the exact position above the Earth and the height of an object, and it tracked in real time. And so that trigger, when that event occurs, all the other data from all the sensors, however many there may be, and there could be up to 6 collections of them, all that gets saved and stored for later analysis by researchers. This is the combination of a optical tracking camera and what we called an MSDAU, and the whole collection is mounted on this very rugged surveying type camera, surveying tripod. The reason why I've been able to accomplish so much at a very low budget is because of the constant march of technology has provided us with tools we could never get in the years past. Very low cost cameras and electronics, sources like Amazon and others for all kinds of different parts and very rapid methods, rapid prototyping for mechanical assemblies like this mount and so on. I've used to the best extent to create this. So this allows us to do the research we need on reasonable budgets, which could never be done before. And the whole point of the architecture is to leverage that to allow researchers in the field at all different levels, from as I said before, just a computer and a very simple camera to, say, 2 of these systems and several different computers, and enable all those people to do whatever work they need to do on a reasonable budget. Okay, so this is the combination of a MSDAU and optical tracking high-end 30 times optical zoom security camera, which is completely environmentally sealed, by the way, to IP67, including a Gore-Tex patch we've added to provide for proper air movement in and out as temperature changes without condensation affecting the camera. The whole camera is mounted on top of this industrial enclosure, which is also completely hermetically sealed except for a similar air movement patch, and which you can see down here. And the interfaces to this box are a waterproof Ethernet connector, the waterproof housing not here right now, and these 2 optional jacks are for external USB devices, such as external RF meters or magnetometers or what have you, whatever we could in the future add as an external data collection device local to the MSDAU. All of the MSDAU is in turn mounted on this ruggedized mechanical mount which interfaces to the tripod. Inside of the MSDAU is a number of devices. One of them, this pair here of circuit boards, the one in the back is a Raspberry Pi, which many hobbyists and others are very familiar with, running a version of Linux and running, again, Python software to implement this remote data collection function. On top of that board is this little board called a SenseHat, which is actually flying right now on the ISS, the space station, but available to everyone, and there's very inexpensive kinds of components, really. But it includes many different kinds of sensors all on one board, ranging from temperature, humidity, a magnetometer, several kinds of accelerometers, both AC and DC, and so on. So if a UFO, if you will, passed over, it might, for instance, modify the magnetic field, or it might modify a gravitational field, which would be picked up by the DC or AC accelerometers. So all of the information is available simultaneously to the mission control over the internet. MSDAU is communicating to the internet over a single Ethernet cable, which might go to a local router or a radio transmitter for Ethernet to a remote site that gets it somehow into the internet. Both power and signal for both the camera and the electronics are carried over a single cable to simplify things. Also in the box is a GPS receiver that is very accurate and exactly places the location of the system, as well as providing accurate time. So when the whole system is closed and locked, it's waterproof, and the entire system can sit out in the field for extended periods of time waiting for an event to occur. This again is one of the primary motivations of the system, that usually when we have any kind of video or camera data, it's just by happenstance. Somebody happened to be in the right place at the right time, whether that area was known to be a hot spot or not, and they just happened to get something. This system we can set up in an area we think is worthwhile placing it there and let it sit there for a very long time, powered by by the AC line power somewhere at the end of this cable, or even solar power local to it. And so over this cable is both the imagery from the video camera as well as all the data from the MSDAU. In different systems, the camera might just sit on a little junction box which interfaces it to a waterproof connector, and there is no MSDAU. Some systems might have only the MSDAU and not the camera. And these could be in different locations in any combination and be doing different things. And as we discussed, we could be adding other kinds of sensors to this. As we said, we'd like to add a simple software-controlled radio to have a complete DC to 2.5 gigahertz spectrum analyzer capability at some point to more completely characterize the electromagnetic spectrum fluctuations that may occur in parallel with an event. I'll first run the software. This is some of the Python. It's all written in Python, which is a scientific programming language used worldwide by researchers for all kinds of purposes. In my case, a lot of called machine vision analysis. And so here we'll run this piece of code. And let me put it over here so you can see it better. This is the GUI, or graphical user interface, of the, what it says up here, OTDAU, Optical Tracking Data Acquisition Unit. You remember I said that the system could receive data from a number of different data acquisition units. That's why the overall system is called UFODAS. It's a data acquisition system which collects data from many different data acquisition units. One type of unit is a computer, a PC in this case, that can run this software. The images that you see on the screen are just CGI, just for fun, just to have something on there before we actually load any particular system configuration. So what we might do is we can go here, and if we click on that, and I'll bring this over here, we can pick a system configuration. There are many different system configurations I've experimented with, but one that we can use right now, because it's in a window that isn't blocked at the moment, is from our tripod-mounted combination of a computer and the other type of DAU, which is the multi-sensor DAU, called it MSDAU, which is the box I mentioned that has some electronics in it. Let's see, that would be this one. So this takes about a minute to get ready, and after I selected that, I can load it, because we can modify the parameters of systems. We can modify what's the definition of cameras, and track various tracking parameters and recording selections, and sharing parameters, like it will share data over Google Drive, it will send an email to anybody we want after a valid collection has occurred, and so on. The system actually can support many different kinds of cameras, old and new, everything, as I mentioned, from cameras that derive from simple CCTV type serial RS-422, 485 or interfaces, or composite video converted to USB. It can support all sky cameras in that fashion, and all kinds of USB derived cameras. In this case, this is a high-end camera, but it happens to be set to 704 by 480 pixels resolution. It could be doing 1920 by 1080. So right now, this is a view out a window, and the blue box is what we call a bounding box, or a crop box, which defines the area of the view that the camera will trigger on when something moves. We have some controls here where we can move the camera up and down, so we can position the initial wide-angle view at the scene that we want to use. Normally we'd position it someplace in a general direction that we think something's going to happen. And then when it's ready to go, we would tell it to run, and it would goes to red, indicating it's now scanning for moving objects. But the reason why I was able to develop this system was because this upper floor window is looking due north, and the path of aircraft flying into Bob Hope Airport is west to east right across my view at about 2,500 feet and less than a mile away. So it's real convenient for getting many, many different test cases. Not to speak of all the other cases, helicopters, birds, small planes, all kinds of things that we have to teach the system in an algorithmic sense to avoid. Of course, doing this kind of work, we're obviously going to catch a lot of false positives. We're going to catch birds that fly by too slowly, although it rejects things that move too fast or flies through the scene too fast. Clouds and bushes that have strange shapes that might emulate the shape of a moving object, and so on. There's a lot of different algorithms involved to help avoid as much of that as possible, and I'm currently working on other enhanced methods to avoid them entirely and reduce a little bit the burden on the user to set certain parameters to avoid them in different lighting and situations. Here's an example that I can play back of what the OTDAU, or the Optical Tracking Data Acquisition Unit software, can record when it notices motion. In this case, it's a jet aircraft, as I mentioned, moving, flying probably about a mile away at about 2,500 feet. And so here it's recognized the object. It shows the minimum, the green box is a minimum bounding box around the actual recognized object, and the red box is a shrunken crop box in which it can detect new motion changes. And you notice that it's occasionally zooming. I think this example, I could probably find some other examples. And this was at 1920 by 1080, so I'm going to run that again. So here it made an initial move, and now it's doing this smooth tracking motion. And you can see its azimuth and elevation are continuously changing. The zoom is up to 3 now. These PTZ activity shows the direction of motion of the pan and tilt function. So let's see, so for example, it can record that with all that metadata, but can also record this view where it kind of removes all that metadata, so you get this kind of clean view. And this view, this recording is, only got up to, I think, what did you say, about 3 times or so. The camera, this camera can zoom up to 30 times optical. It works night or day. This is looking out that same kind of window at night. There's a really small object that it's tracking. This object is not moving very fast, so it's capable of zooming in longer. And sometimes it goes out of focus as it zooms, but it sticks with it anyway. Sometimes you see other little things on there. Some things like this may seem to move, but the reason we have these indicators is you can tell the difference between the camera motion and object motion. There's another jet. Zooming in on it. It zooms incrementally. The objective of the software implements a closed loop pan tilt feature where it's always trying to move the object to the center field of view, because obviously when you try to zoom and you're not in the center field of view, the object will go shooting off one direction or the other. So it moves, zooms, moves, zooms in sequence like that. And here, ended up the bounding box got caught in a tree, so to speak, and and that's where we go. So in this case, this is what the unencumbered view looks like without the metadata display. It also has a feature now where I call auto cruise, where if it does encounter an object, like it goes behind a tree or a bush, it's always computing the velocity vector of the object, and it will try to continue the motion of the camera at that velocity vector, even though it's not really detecting the true object anymore.
Nice.
So it'll try to keep it in view of some sort as long as possible. Okay, so we're demonstrating in a fashion the way the system triangulates information from two different cameras. Here's camera 0, here's camera 1. The information is sent over the internet from the camera, which consists of its azimuth and elevation. In other words, the azimuth is left to right where it's pointing with respect to due north, and its elevation, which is tilt angle of the camera, compensated a little bit by calibration. And also the actual location of the camera in longitude and latitude that might have been derived from an address and geolocated, or the longitude and latitude numbers directly put in. In any case, when both cameras are triggered, this is triggered, this currently says false, but if they both saw a moving object at the same time and their paths of their view angles crossed, then the system would look like this, where it computes the latitude and longitude of the target object and the altitude of the target object. The other boxes here, they could be these MSDAUs with all the data that they accumulate. When it does that, it has a whole bunch of lines of data of all the different kinds of sensors that, that the thing is collecting. This is the a kind of data that the emission control can collect when it is triggered and when it's collecting data. These are file names. This first one is an AVI, a video of this Google Maps screen with all of the metadata on it in real time. So as the triangulation is moving, all that's captured in real time into a file that can be played back, which we're going to do. It also can simultaneously collect the actual video streams from the two cameras that are contributing to that triangulation. The mission control establishes, in parallel with OTDAU, its own video stream to those cameras, and that's what it's using to record, and that's what it's using to give these thumbnails of what those cameras are seeing. So someone in mission control can say, wow, look, I can see this object, and this is what it's recording, what's causing it to triangulate. So for an example, if we look at this recording, here it would be as if there was an object at roughly 7,000 feet moving around. The blue lines or green lines turn into red lines, the T becomes red, and it kind of indicates where the object is moving until it becomes out of view of either one or the other or both cameras. Okay, so this is the mission control application. And as I mentioned, mission control is this kind of software where one might have one copy of this running at perhaps a central location, like something you consider mission control, where you're in touch with field observers or sites where there's OTDAUs or MSDAUs, and you've defined some kind of a scenario where you have multiples of those devices, and as many as 6 of them, 6 collections. Each one's called a data acquisition unit, DAU 0 through 5. Each one of these could be an OTDAU like we were just looking at, or they could be a MSDAU, one of which is here that's not mounted in a box. The green or red arrow is indicating it's sending data through the internet to a remote site like mission control. And all of these little boxes, all this stuff would be in an enclosure we're going to see in a little bit. And this, by the way, this device here is a tri-field meter. One type of data source uses this antenna to collect electromagnetic changes, and those electromagnetic changes are converted to digital by this device, and it's yet another type of data that the MSDAU can collect and transmit to mission control. In the future, we may have more sophisticated electromagnetic spectrum measurement devices that use software-controlled radio. Notice I can run multiple copies of different kinds of software on one computer. We're not constrained to having to use different computers just because we're running different applications. And there, what we see is basic location information, azimuth and elevation and zoom for each of these two cameras. The location here is in longitude and latitude, which is derived from actually telling the system where the physical location of those cameras are. You can just give it a street address, just like in Google Maps. It uses the Google Map API actually to do that, and here when we run the application, there's the Google Map, and there's the actual real-time video from both of those cameras. And if we move one of them, we'll go over to, let's say for instance, we physically move this one. You can see the camera's moving here, the image is moving here, and the azimuth, because I'm saying turn right, so the azimuth changes to indicate, and this green line, I'll get this out of the way, this green line shows the track or the azimuth direction that the camera's pointing. Ordinarily, we would start by pointing both cameras due north and as far down on the horizon as we can, and the OTDAU software allows us to set that as the compensated position. So from then on, the system recognizes in absolute coordinates appropriate for geolocation where the camera is pointing. And so, for example, if we continue to move right, then we can point, wherever it happens to be. If the other camera, let's say the other camera moves likewise, let's see, oops, we had to stop it. We'll move this camera, and now it's moving. Now the aircraft that we're interested in, typically, here's Sherman Way, the aircraft fly this direction right along here at about 2,500 feet. I can put this system in this setup menu into a test mode. In test mode meaning we kind of fake it out, and we say we're not going to worry about actual, what do the cameras actually see, but only the fact that the two lines cross, emulating triangulation.